Hello and welcome to ion exchange, or in layman's terms, water softening. The softening exchange process, how does this actually work? Well, the hardness in the water passes through a resin tank and ion exchange resin beads. They're essentially a styrofoam bead that's impregnated with sodium ions. And the calcium, magnesium, and iron are exchanged for the sodium. If you notice here, for every one of these +2 molecules, we push off 2 of the sodiums. The charge is equal. So it's sort of a magnetic exchange. This is a stronger magnet than these 2 guys combined, so it's able to push them off. The same thing that happens with the iron and the calcium here. And when the resin has no more sodium left on those resin beads, the softening exchange process must be reversed. And that's known as regeneration, or regenerating the softener. And a good system means a balance between minimal regenerations and optimal production, so we don't waste water or salt to regenerate that resin. Now, this is how it works on a chemical level with sodium-based water softening. And that's the type of resin that's inside the softener. It's a sodium-based, or it can be a weak acid-based when we're talking about cation exchange, which is water softening. And what goes on here is as we soften the water, we're going to remove these +2 minerals. Sodium and potassium, notice, are +1, and they're not exchanged in this process at all. So as the stronger magnets or bigger plus-charged metals in the water come in contact with the resin, which is represented by the R here, you get an exchange. For every 1 calcium that gets bonded to 2 of the resin molecules, you get 2 sodiums to come off. And as you can see here, what ends up in the softened water is the potassium in the water and more sodium. And notice, it does nothing for the anion or the negative charged particulates in the water. Now, water softened resin, cation resin, is regenerated with sodium chloride. And what softeners will remove from the water, it's important with regenerated with sodium chloride. In a water softener, you want to use salt that is specifically labeled for use in a water softener. Rock salt for melting ice in the winter, if you live in a northern climate, is not suitable for this purpose because A, it's a mix of many, many different salts, and B, it's very, very dirty relative to this, and it ends up clogging the softener and causing issues. But what softeners will remove from the water, and it's in a preferential treatment of selectivity by charge. It will remove most of the metals in an ionic form in this order, starting with aluminum down to barium, strontium, zinc, copper, iron, manganese, calcium, and magnesium. And then notice we have potassium and sodium down here. And there are 2 other forms. There's another form of resin that's an acid form, which will remove sodium also. So cations, or metals with a higher charge, are removed first. These are the bigger, stronger magnets, so to speak, that will push off these smaller, lesser charged magnets, so to speak. Now, how do we size a water softener? There are 6 steps to sizing a water softener. First one is we need to test the water hardness. We need to know how much hardness we are going to exchange in the softener. And then we have to determine the pipe size, whether if we're just feeding a hot side, feeding a water heater, we need to know what plumbing feeds that water heater and match the softener to that flow of that plumbing. And also, it is very important to the exchange process for a water softener to have the pipe size coming into it match the plumbing on site so that the flow rate over that resin is within a specific range. Because if we move water too fast through a water softener, we don't get the contact time we need, and we end up with shorten gallon capacity because the water is moving too fast through it and hardness leaks through. And if we go too slow, we'll cause channeling through that bed and we'll get hardness to leak through before we do any real exchanging. And then we need to understand daily water use. We need to know this because we need to know how much hardness we're going to remove on a daily basis in order to size the capacity of the water softener resin tank. And then from that information, we're going to calculate the volume of resin we need for the regeneration schedule we would like, whether that's daily, once a week, twice a week, and we can size those things according to our customers' desires. And then from that information, we're going to choose a tank configuration, whether it is a single tank water softener or a twin tank water softener. And then from that determination, we're going to select the model of the water softener. So how do we do that? Well, first we have to start off by talking about flow rates versus pipe size. The green chart here is maximum hot water flow for the piping, and the blue is the maximum flow for the cold water piping. So there aren't too many very effective hot water softeners. So what we're going to do is select the cold water flow, and we're going to see that the pipe size, the flow rate involved, is going to line up here. So for 1-inch copper, we have 7.8 feet per second with a pressure drop of 8.4 psi per 100 feet of plumbing. We want to take this into account so we get those flow kinetics right. So this is why matching that pipe size is important to the selection of a softener. And then we have tools in technical service and the ROM team that can help you size water softening. And typically in commercial applications, we're going to deal with softening the hot side only because it's fairly rare that we would need to soften the cold water side as well. And you can get estimates on the amount of water they're going to use per day based on the type of restaurant it is, or bar, or hotel, or hospital, based on the number of beds. We have estimators for this because sometimes getting water usage data is difficult from an end user. And then we have tools that are also available that allow us to size a softener based on those covers per day, the hardness included, and we're able to calculate that usage to about 5,000 gallons per day. And we have a tool that will select the proper water softener and the properly sized 7 cubic foot water softener. And we can select the same one for the twin version of the unit based on those same numbers. And the difference between a twin and a single water softener is going to be about a 20% difference in saving of water usage and salt usage between the two designs. So what we need to know to determine what's needed, we need the grains per day, which is the amount of hardness in the water, times the gallons per minute times hours of operation. So we have 11 gallons per minute times 60 minutes times 16 hours of operation. We're going to need to remove 10,560 grains per day of hardness. So you take the grains per gallon times the grains per gallons per day used is equal to grains consumed. So you have 17 grains per gallon hard water with 10,560 gallons per day being used, and you're going to need a softener that can handle 180,000 grains per day. And we're going to select a softener based on its capacity, and the closest one that matches us to our needs is a 7 cubic foot water softener regenerated either with 15 pounds per salt or 9 pounds per salt per cubic foot, somewhere probably around 12 pounds of salt per cubic foot would be perfectly sized for 180,000 gallon grains per day capacity. Now, once we've determined the water chemistry, pipe size, flow rates, hours of operations, we need to know utility locations where we're going to install this system, where we're going to need to have access to cold water inlet, an electrical outlet depending on the power rating of the head involved, whether 115 or 220 volts. And we're going to need a drain that can handle the backwash flow rate of the softener. And then we're going to need accessibility to the brine tank in order to keep filling that brine tank with salt, because the salt in this process is a consumable. We're exchanging it for the hardness, which we're sending to waste when we regenerate the system. And also, the unit's going to need to be serviced periodically for preventative maintenance issues or potential failures to be able to access the head of the softener. And then we're going to need to know entry doorway dimensions, because some softeners get rather large and may not fit through a standard man door. So that may limit our selection of what size softener. We may have to go with a twin tank softener of smaller tanks to meet the same capacity because we couldn't get the softener through the door. Or you'll have to note whether if there's an overhead door that can be gone through to enter the building. And then we need room dimensions, the physical space for the softener and its location, and whether it needs a rack to meet health codes or not to get it up off the floor. Those things are all considerations we have to take into account. So in a cation exchange softener, what happens with the chemistry involved and the measurements we're going to see? Well, when we do a sodium exchange, you're actually going to see a slight increase in total dissolved solids because we're exchanging 2 sodiums for every 1 calcium. And sodium has a particular chemical effect that it's able to conduct electricity a little bit better than calcium. So you get a slight bump in the level of TDS. And the same thing happens here when you regenerate with potassium. Now, weak acid cation exchange softening, better known to you as Claris, is instead of using a standard sodium-based resin for an exchange process, we are going to use a weak acid cation exchange resin that donates acid to the water instead of sodium. And you're probably wondering why we would wish to do that. It's because we're taking advantage of the alkalinity buffer system to remove some of the alkalinity as well. This allows us to do partial softening and partial bicarbonate reduction. So what we have here is that same reaction we saw before, but instead of sodium here, we have 2 hydrogens. And when they're released as H+, which is acid. It's what we measure when we measure pH, is the concentration of this. So we have acid released to the water. Well, now, we're going to do something with that acid. Since we've partially softened the water with the bypass feature of the Claris, you're going to leave some of this mineral content behind. But notice that the alkalinity has been reduced. Well, that alkalinity gets converted to dissolved CO2 gas, which will then bubble off, hopefully causing the pH to rise back up and giving us a balanced pH. If you notice, we have 2 acids here plus 2 bicarbonates. And this produces 2 CO2 gas molecules and 2 molecules of water. This is the same thing that happens in your stomach when you take a Tums, bicarbonate. You're taking that to neutralize your stomach acid, which is causing you discomfort. Well, after you take Tums, you have to burp. That's CO2 coming out of that reaction. We're exploiting that same chemical reaction and process here to lower the hardness minerals and get rid of the other part of the recipe that forms scale. Now, there are places where you wish to use Clarus and where the use of Clarus is not appropriate, and that's due to that generation of acid. There are other things in the water that are going to compete for its attention in the water. And let's note as we take a look at this water analysis, the pH, the TDS, the chloride, and the bicarbonate. Notice the pH is 7.8, pretty basic for drinking water. And we have rather high TDS of 785. But notice that we have a lot of chloride in the water, and that's 258 parts per million. And that's rather high from a corrosion standpoint. And here we have the bicarbonate, which is that buffer to those corrosion factors. We have that here. Now look what happens when we apply Clarus with a zero bypass to this water. So what's going to happen is we're going to produce that acid, but instead of getting a balanced pH, that chloride and sulfate and nitrate in the water compete for that acid, and we get a possible pH drop down to 4.3 to 5. That is very, very acidic water and very aggressive and really isn't considered potable. So we don't want that sort of drop in our water because this is going to be aggressive to the equipment as well. So we have to be careful on applications when selecting Clarus and the chloride levels. It may direct us to the use of other Clarus tools like Ultra or Clarus Prime that can help us manage these systems. But putting Clarus without looking at this water chemistry first can be problematic. Notice that the bicarbonates are dramatically reduced from 217 down to 16 parts per million. The Clarus is doing its job because that's what it's supposed to do, reduce bicarbonate. And it's reduced the TDS level similar to the bicarbonate reduction, 785 to 585. And notice that we've partially removed some of this hardness as well. It's doing its job, but nothing affects the chloride level coming through. The pH is much more acidic. In actuality, almost 20 times more acidic than it was before, as acid was created by the chloride ions interaction with the hydrogen released and the removal of the bicarbonate buffer system. So Clarus and weak acid cation exchange technology must be used and selected for the appropriate water qualities. Now, Clarus has a younger brother called Clarus Ultra, and it takes advantage of this partial softening and weak acid cation exchange resin, but the bypass is slightly different. It actually bypasses more water and keeps more mineral content in the water. So you get less of that acid created and only partial reduction in the alkalinity. So you get a pH drop that is managed within potable ranges and suitable for most of our applications at a 60% bypass. So what this does is allows us to leave some of that Tums in the water to combat the acids that are going to be formed. But since we've left some of the recipe in for scale, it often also offers some sequestering with phosphate to control that scale buildup. And as we see here, the rest of the calcium that isn't removed by the cation exchange resin is going to be sequestered by the phosphate, which will tie up a significant amount of the calcium, preventing it from hard scale. So what you get with a 60% bypass is a reduction in TDS from in this case, 356 ppm down to 214 ppm, while we're leaving some mineral content in for the application. Now, what's great about Clarus Ultra is it stabilizes that pH drop. As you see here, here's the pH of the water tested in the same application as it's being used in the application. And over time, you notice that the Clarus Ultra's pH management is nearly linear, which shows it is holding a very consistent and true pH that won't go out of range and cause issues. So where Clarus is useful versus where Clarus Ultra is useful. useful. Clarus has applications in drip coffee, espresso and tea, and brewing equipment, and combi steamers, steam ovens using boiler-based systems without high chlorides and silica in the water. So Clarus will work as long as we don't have high chlorides and silica in the water that will prevent us from meeting manufacturer's warranty spec and create a pH drop and a corrosion issue based on the incoming water chemistry. If the water is good for selection of Clarus, it's appropriate for any of these applications. Now, Clarus Ultra has application in drip coffee, espresso, tea, brewing equipment, and small ice-making equipment. Please notice the absence of combi steam ovens. Any direct injection oven should not be using phosphate in it because phosphate needs to be in solution to work inside the water. Well, direct injection steam equipment vaporizes the water on contact, so the phosphate can no longer function. So it's basically useless in this environment. And on top of it, that phosphate will cause a thick sludge if the oven's being used to cook proteins. So we don't want to create more of an issue maintaining that oven than we normally would based on its water chemistry. If you have a boiler-based steamer, Clarus Ultra will work. Now, compared to its competition, Clarus has many more features that are at a higher level than any of its competitors in the marketplace. So from quick change to a built-in adjustable bypass head to adaptation and stabilization of that adjustment, our adjustments stay locked in truer than any of our other competitors. And we also offer a little bit of corrosion inhibition due to this balanced approach to managing the water.